Dr. Maryjo Brounce's PhD student, Jen Humphreys, is going to introduce her for us.
Hi, everyone. Good morning. So today I'd like to introduce Dr. Maryjo Brounce. She's an assistant professor here in the Department of Earth and Planetary Sciences at the University of California, Riverside. She's an igneous petrologist and high temperature geochemist. She earned her PhD from the University of Rhode Island's Graduate School of Oceanography, where she worked on oxidation state of iron subduction on rocks with PhD advisors Katie Kelly and Liz Cottrell. Maryjo went on to a postdoc at the California Institute of Technology, where she worked on the iron sulfur oxidation states in ocean island rocks with Ed Stolper and John Eiler. In addition to making new measurements on these rocks, she also pushed to make connections between the oxygenic acidity in the solid earth and the partial pressure of oxygen in surface environments. This is the topic with which she'll be talking to us about today.
Thank you, Jen. And thanks to Andre and Alex for the invitation and for everybody for being here today. In whatever time zone you're in, good morning, good afternoon, or good evening. So the title of my talk today is going to be about the oxidation states of iron and sulfur in Hawaiian lavas and what we've learned from those about the role of volcanic gases in Earth's oxygenation. This is work that I did. I was a postdoc at the California Institute of Technology from 2014 to 2016, and this is the measurements and the thought process here is some of the stuff that I was steeped in when I was there. And so when Andre asked if I had any connection to Precambrian geology, if there's anything that I thought might be interesting for you folks, this is immediately what I thought about. And so I'll tie it through. I think I've kind of shuffled the sulfur stuff to the end, just in case anybody's interested. I'll focus on the iron story because that's, I think, some of the most robust measurements and the most interesting avenue of connection for people here today. The rocks that I actually measured are basaltic pillow lavas recovered by the Hawaii Scientific Drilling Project, which drilled into Mauna Loa and Mauna Kea basalts on the main island of Hawaii in the late 1990s. And they drilled down in Hilo, Hawaii, and recovered a really remarkable set of lavas. This is the drill rig on the left-hand side photo. And on the right-hand side, this is just an example of some of the box core pillow textures that you get. And some of these pillow lavas had pristine glass preserved on the surface of these pillows. And the glass shards are the things that I've made these measurements on. Okay, so I want to begin. I think everybody here is used to thinking about oxygen in surface conditions, and I want to talk a little bit about oxygen in the solid earth because it behaves a little bit differently than what we're used to thinking about in the surface conditions. And I'll start with the idea that I am interested in oxygen on Earth, as everyone else, I think, in the room here is, and I'm interested in the role of oxygen in promoting some of the formation and differentiation series for our solid Earth body, and what the distribution, not only the abundance, but also the reactivity, the activity, or the fugacity of oxygen in the solid layers, as we moved from a situation on the left in this cartoon where we were in a accreted body from primordial solar system materials, where I'm showing, you know, in the earliest stages, iron metal is disseminated throughout our body. And then eventually over the course of geologic time, we segregate a metallic, iron-rich metallic core from a silicate mantle and crust, and eventually give rise to the stable oxygen-rich and water-rich conditions at Earth's surface. And so I'm interested in understanding in the solid portions of this what the distribution of oxygen and the activity of oxygen between these layers might be, and how the activity of plate tectonics and geologic processes unique to Earth have been mixing materials from the surface in the interior, and how those signals, we might pick them up in the rock record, in the igneous rock record. Okay, so what do I mean when I talk about the availability of oxygen? I'm going to start with this list of the 8 most abundant elements in the bulk Earth. This comes from Bill McDonough's work on this topic, and you'll see that oxygen is on this list. and it's really high on the list. This is a really important point. There is an enormous amount of oxygen bound in solid earth materials. There's an approximate sign here, a little tilde, because in part it matters how much oxygen you think might be dissolved in the iron metal in the core, which is an active area of research now. But whether there's no oxygen in the core or a lot of oxygen in the core, this number competes right here with iron as one of the most abundant elements by weight in the solid earth materials. That's the crust, the mantle, and the core. In the solid earth, though, most of that oxygen is bound as the electronic balance to oxidized versions of everything else on this list, with the exception of sulfur. So, for instance, silica, we have quite a lot of silicon bound in the solid earth, but it doesn't exist as silicon metal. It exists as silica 4+, a 4+ cation, and oxygen serves as the primary balance here to form the silica tetrahedron, which is this unique chemical structure that gives rise to the great variety of minerals that we see on this planet and other planets in our solar system. These oxygens are hard bound to those silica cation centers. They're not free to move around and to participate in chemical reactions. It is very difficult in the conditions just about anywhere in the solar system, in fact, at least today, to reduce silica from its 4+ state, thereby releasing an oxygen. So you're stuck with silica 4+, and those 4 oxygens are stuck with that silica 4+ cation. They can't move around. They are not available to participate in reduction oxidation chemistry. Same is true for magnesium. Iron is a little bit different. We can kind of switch between iron 2+ and iron 3+, and so there's a little bit of motion of oxygen between these two elements over a variety of rock forming environments on the Earth. And this is actually what I'm going to leverage, because it turns out to be very difficult to measure this activity or the availability of oxygen, because most of it is tied up. But what we can easily interrogate is the relative proportions of ferric and ferrous iron. So this is really different, of course, than in the atmosphere. There is much less oxygen by abundance bound at the surface of the Earth, in the oceans, in the atmospheres, in the rivers and soils. Significantly less than what's bound in the solid Earth, because the solid Earth is just so huge and there's so much oxygen there. However, the oxygen that does exist at the surface exists as the dioxygen molecule, which is very reactive, very, very reactive. And it readily interacts with, for instance, iron metal, and oxidizes it to ferrous iron, and then further to ferric iron. This is what causes rust in, I'm from Philadelphia, and this is part of like the Rust Belt of the United States. And so everything was made of steel, and the iron in the steel has been oxidized and rusted. And so buildings, bridges, things like that are rusted. And that's due primarily to the very active nature, very available nature of what oxygen is present to participate in reduction oxidation chemistry. Okay, so we've got this kind of contrasting situation where the solid Earth has an enormous amount of oxygen, but a very, very small percentage of that is available to participate in reduction oxidation chemistry. And in the surface, there's much less oxygen, but just about everything is available to participate in reduction oxidation chemistry. So if we were to think about this, try to track this amount of active oxygen as, for instance, the partial pressure of the O2, the very active oxygen molecule. If we were to keep track of that, it would look something like this. So this is a diagram of the log of the partial pressure of the dioxygen molecule along the x-axis here. And the Earth's atmosphere plots over here to the right, where we know that the partial pressure of oxygen at sea level is something like 0.2 atmosphere, and the log of that value is just above a value of -1. And so Earth's atmosphere is over here to the right on the diagram, and we would call that oxidizing. This is a level of concentration of active oxygen, so to speak, that would promote a lot of reduction oxidation chemistry at 1 atmosphere, 20 degrees Celsius. The amount of this available oxygen in terrestrial basalts, though, is 7 orders of magnitude lower. So this is kind of an average value for basalts that erupt to the surface of the Earth, and they reflect the availability of oxygen of their mantle sources. And so again, even though this rock is 30 or 40% by weight of oxygen, so much of that oxygen is bound up that there's only about 10 to the minus 8 available to participate in reduction oxidation chemistry. And so this is where basalts that are up to the surface of the Earth fall. Basalts that erupted to the surface of the moon that paved the lunar surface are even more reduced, about 4 orders of magnitude lower in this partial pressure of oxygen metric that we're using. And it turns out that lunar basalts are very close to this equilibrium that exists between metallic iron and iron oxide, the mineral wustite. And in fact, you can find blebs of iron metal present in lunar basalts that you don't at least commonly see in terrestrial basalts. It's important to remember that this is a log scale, so I'm going to be talking about orders of magnitude difference today, so that if the Earth's atmosphere is over here just above -1, terrestrial basalts are going to be 7 orders of magnitude more reduced, and lunar basalts will be 11 orders of magnitude more reduced than the conditions at Earth's surface. I'm also going to use a reference frame here so that we don't have to talk about like logs or 10 to the -8s or differences between very small numbers. This is called a solid oxygen buffer, and it's the equilibrium between, I'm showing you olivine, this is the phthalate component of olivine, and oxygen. Equilibrium between those two components and silica or quartz and magnetite. And the idea is that if you know the activity or the concentrations, the concentrations of each of these mineral components of magnetite and quartz and phthalate, and those conditions, your partial pressure of oxygen is fixed, and the equilibrium can shift to adjust as the abundance of each of these mineral phases changes. Because this buffer has quartz and phthalate and magnetite present in it, we call it the quartz phthalate magnetite oxygen buffer. And it's a useful metric in part because it happens to record a log partial pressure of oxygen in solid Earth temperatures and pressures that correspond to that recorded in terrestrial basalts. And so essentially this is just like choosing a 0 value adjustment, like a stable isotope geochemist would choose standard mean ocean water or something like that. We're going to use QFM like that. So that 0 is going to be this value of around 10 to the -8. And then I can reference from that value in on this log scale. So for instance, the difference between 10 to the -8 and 10 to the -12 here, I could call QFM -4, 4 orders of magnitude lower in this partial pressure of oxygen than the value recorded by terrestrial basalts. And then in the reverse direction, for conditions that are more oxidized, I could say that the Earth's atmosphere is just above QFM +7 or 7 orders of magnitude higher in the log partial pressure of oxygen than recorded by terrestrial basalts. Okay, so this is how oxygen behaves in the solid Earth. That's our crash course. And here's what we know about it. I would say if you collect everyone who works on the problem, all of the igneous petrologists into a single room, I think everyone would broadly agree to the constraints on this cartoon. Where on the left-hand side, when we accreted from early solar system materials, the solid Earth in a bulk sense recorded an FO2 not higher than that value of QFM -4. And that's because a lot of models for early Earth formation and differentiation start on the hypothesis, that iron metal was disseminated throughout the body, like in that moment before core formation. And so we've got to be in reducing enough conditions to stabilize the presence of iron metal. And then as we move forward in time, we form a core. The conditions at the core mantle boundary have got to be in the neighborhood of QFM -4 because we've got iron metal present in the core and iron oxide, potentially wustite or other ferrous iron oxide minerals present in the lowermost mantle. Big question marks about the activity of oxygen in the lowermost mantle, tied really closely to uncertainties in just the major element composition of the lower mantle. There's a lot of uncertainty here. The surface condition we know pretty well is near this value of QFM +7 today. Of course, there's a lot of interest in this room as to what that value was moving back through time. And then as you approach the kind of crust and uppermost mantle, the place where we have the most samples from, we agree we are close to this value of QFM, kind of plus or minus 3 orders of magnitude. And so that is sort of the level at which we think we understand the distribution, the variation in activities of oxygen in the solid Earth. And so this is where I spend most of my time working when I'm thinking about rocks from this planet, is trying to narrow these constraints or understand what drives that variability. Now, the cartoon that I've drawn here is like a static image, especially the Earth on the right-hand side. And of course, we know that the Earth's surface and interior is not stable, not static. And in part, one of these interesting things about the Earth in terms of igneous, metamorphic, and sedimentary rock formation is the presence and longevity of plate tectonics, which causes physical mixing and interaction between layers on the Earth. So there's a lot of mixing happening. And the idea here that I'm showing, there's a couple things that I'm showing here. The first thing is this, if we go back to this QFM plus or minus 3, what is becoming apparent, or one emerging hypothesis that explains this uncertainty or this range we think we see in the activity of oxygen, is that the activity of oxygen in the solid Earth varies, and it varies as a function of tectonic setting. And this is something, there's a AGU monograph chapter in press, and it's been in press for quite some time, but it's up on like the EOS archive. If you're interested in this idea, you can go look at a compilation of data that suggests this is true. The idea is that the normal upper mantle that feeds divergent boundaries at the mid-ocean ridge is reduced, relatively reduced. It's this value of QFM, and that's what we make the ocean crust out of. The ocean crust then gets exposed today for an average of about 65 million years to the high oxygen activity conditions of Earth's surface and deep oceans. And hydrothermal alteration and oxidation, oxidative weathering, and deposition of oxidized minerals takes place in the sediments and the crust and the mantle lithosphere underneath of it. And so this plate gets hydrated and it gets oxidized during that time exposed at the surface of the Earth. It comes to a convergent margin and it subducts. That oceanic plate returns back to Earth's deep interior. And as pressures and temperatures squeeze on that subducting plate, prograde metamorphic reactions drive melting and water loss. That ocean water gets squeezed out of the plate and it percolates upwards into the mantle above subduction zone settings. And we think that that increases the activity of oxygen, that some portion of the oxidation that happens at Earth's surface gets squeezed back out with the water, with the trace elements, with the isotopes that we know get squeezed off of this lab, and ultimately contributes to an oxidized nature of arc basalts here. And then there are back arc spreading centers that are kind of intermediate in oxidation. I'll just remind you here again, we're talking about orders of magnitude, right? So arc mantle is somewhere between 1 and 2 orders of magnitude more oxidized than the normal upper mantle as the direct result of this interaction with material derived from the surface. And then back arc is a little bit less so. And then there are ocean islands, these so-called hotspot settings like Hawaii, Iceland, the Canary Islands, French Polynesia, places like this, where we find also a variation in the activity of oxygen in the sources of these, where some places look to have activities of oxygen similar to QFM, so just like normal upper mantle. And some areas look to be more oxidized, 1 or 2 orders of magnitude higher in activity of oxygen, tied to the possible presence of ancient recycled subducted plates here. So the plate gets formed, it interacts with the surface, it gets oxidized. It subducts, some of that oxidized signature comes out immediately in arc volcanoes, and then that slab continues down into the deep mantle, potentially to the core mantle boundary, where it can be entrained in upwelling mantle plumes and erupted here at ocean islands. And the ocean islands, it seems, that contains these signatures of ancient recycled surface materials are record higher activities of oxygen. So we're seeing this kind of solid Earth oxygen cycle that is tied to the surface oxidized conditions. This is something I was thinking that I'd talk a little bit more about this, but the manuscript is still in revision, and so I'm just going to mention this as something interesting for this crowd. Here I'm showing you what is being called the lead model age, and this comes from a paper published in 2015. This is the lead model age of the subducted component at a variety of ocean islands. And so if the ocean island over here behind the words, you can see I've got little like squigglies. If those squiggly lines ultimately are bits of ancient subducted slabs that used to be at the surface, if we look at the lead model age of that enriched component, we see a distribution that looks something like this. I'm going to talk about Mauna Kea basalts here. And so the Hawaiian Islands have this enriched isotopic component that looks like ancient subducted material, and that ancient subducted material was at the surface about 1.5 billion years ago, on that order. As we look at the distribution of lead model ages, and there's some uncertainty here, but two places stand out here. Number one, Samoa, and number two, Reunion Island, where the lead model age for Reunion Island happens to be right at or just prior to the Great Oxidation event, the arrival of clear chemical signatures, isotopic and redox sensitive trace elements, things that everybody here is very interested in. Records for the timing of the arrival of significant oxygen accumulation in Earth's atmosphere and surface conditions. And that recycled component in Reunion mantle plume predates that Great Oxidation event, or is at least contemporaneous with the very beginnings of it. And when we measure these Reunion Island lavas, we find out that they're not oxidized, that they look like this QFM. And so that is really encouraging to us that there's a strong tie between the activity of oxygen recorded in igneous rocks being erupted today and the timing and the history of elevated partial pressures of oxygen at the surface at times in the past. But unfortunately, I won't talk about Reunion today. I'll focus on Mauna Kea for the rest of the talk. Okay, right, so that's what I'm going to talk about. And the idea here is that there's some kind of link or trying to poke at what could be the links between the partial pressure of oxygen at Earth's surface and the activity of oxygen in Earth's interior, or something about how the activity of oxygen changes during igneous rock petrogenesis. And on the top panel, I'm showing a figure from Tim Lyons that is probably familiar to everyone. This is the log of the partial pressure of oxygen in the atmosphere at Earth's surface as a function of geologic time. Time on the x-axis in billions of years, where present day is on the right, and 4 billion years ago is on the left-hand side. And the black and the gray lines, solid curves, are showing what we think is true from a compilation, a variety of measures of sedimentary rocks at Earth's surface, about how that partial pressure of oxygen at the Earth's surface has changed, where we have very low values persisting for some time. Around 2.4 billion years ago, there's a onslaught of evidence from mass independently fractionated sulfur isotopes and redox sensitive trace element abundances and ratios to elements where we expect them to behave similarly in sedimentary rocks that indicate an accumulation of oxygen at a level at least sufficient enough to form an ozone layer at Earth's surface to stop these photolytic reactions for the sulfur isotopes, for instance. We persist at some intermediate level. The difference between the black and the gray line here could be a hypothesis about the partial pressure of oxygen and in the Earth's atmosphere, but also potentially a difference between the value in the atmosphere and the value in the deep oceans for a long period of time. A second rise in oxygen, and then a leveling off at values that are familiar to us, where we live just under the value where like everything burns. That is fine, but where the puzzle lies is in the timing from the chemical fossil rock record of the beginning of oxygenic photosynthesis. And so if the partial pressure of oxygen we have today, although it's a somewhat complicated cycle, is ultimately driven by oxygenic photosynthesis, then we would expect the big rise, the big driver in the rise of oxygen in Earth's atmosphere to be the arrival of oxygenic photosynthesis to the surface of the Earth. And it turns out, a little bit puzzlingly, that it seems that that oxygenic photosynthesis predates by something like 500 million, a billion years, predates the Great Oxidation Event to some extent. And this has been something that I think a lot of people in the room have dedicated a lot of time and thought to understanding. Why do we not accumulate significant oxygen in the atmosphere, and in the same moment we begin to be doing oxygenic photosynthesis at Earth's surface? And there's a lot of avenues to pursue here. The solid Earth, looking to the solid Earth, is just one avenue. And so there's been what I was thinking about when I was a postdoc at Caltech are the times that people have tried to make links between solid Earth oxygen fugacity and surface partial pressure of oxygen to understand if there might be some change in something happening in the solid Earth at some deep level for some thermophysical reason that might cause this. And so the question at first is, was there a change in the solid Earth oxygen fugacity around 2.4 billion years ago that would have changed a major source of the volatile elements that get degassed by volcanoes, carbon, hydrogen, oxygen, sulfur, to the atmosphere that would have suddenly permitted the accumulation of photosynthetically produced oxygen? And this is a question that Dick Holland and Fabrice Gaillard, a bunch of people have thought about investigating. And what we have today are a number of proxies or ways to get at this activity of oxygen in the solid Earth, especially in ancient rocks. What I do in modern rocks is relatively straightforward. Getting at the ancient rock record is significantly more complicated because of the textures that are preserved and the metamorphic histories these rocks have gone through. But nonetheless, people are able to make careful measurements and place constraints on what the oxygen fugacity in rock forming environments would have been at times in the past, so that we can make a plot that kind of looks like TIMS, but with a lot fewer constraints in any time older than about, I don't know, 50 million years ago. So everything over here is really well constrained, and then everything else is more difficult. But what we see, and this is the log of the activity of oxygen. This is relative to that QFM oxygen buffer. So that value of 0 is what we expect kind of normal mid-ocean ridge basalts to be doing. Subduction zones are a little bit higher. And what we see through Earth time is that there's not really any evidence that there's been major changes in the activity of oxygen in the solid Earth that has been producing basalts or komatiite, some kind of igneous rock that gets then erupted to Earth's surface. So that does not seem to be the case. It's not borne out in the igneous rock record or the metamorphic rock record that we have available to us. So the answer to this first question, is there a change in solid Earth FO2 at any particular time? The answer seems to be no. And this continues. People are now working on rocks a little bit more leading up to this area, and there's some question there, but there could be some trajectories, positive or negative trajectories happening in this period of time, but there's not, for instance, anything happening below this value of QFM -2, which I'll show by the end of the talk is kind of a magic number. There's nothing that was more reduced to that than that and then becomes oxidized at the time of the Great Oxidation Event. So then the question comes, well, then how else can we change that volatile load? If the point is that we need the gases that erupt from volcanoes to change in principle so that what gets emitted ultimately to the atmosphere looks different, we can do that by changing the activity of oxygen in the solid Earth. Maybe there's not a lot of great evidence for that. We can also do that by changing the pressure that these volcanoes degas at, because the gas phase is extremely sensitive to pressure, and the composition of the gas phase is extremely sensitive to pressure. And so it could also be, the question then became, is there a change in the average pressure of volcanic degassing around the Great Oxidation Event that would change the major source of volatile elements to the atmosphere that permit the accumulation of photosynthetically produced oxygen? And that's what I'm going to get at today. And at the time this question was being asked, 10 or 5 years ago, something like that, the idea is this. So I've got a cartoon magma chamber over here to the right. And the idea is that at high pressure, like in the mantle and in the deep crust, these silicate magmas have dissolved in them some amount of carbon and hydrogen and sulfur and oxygen associated with those species. And then as that magma rises up in the crust into volcanic edifices to erupt, the pressure gets released. The pressure of the overburden of crustal rocks diminishes. And as that magma reaches surface pressures, 1 atmosphere, remember it's at 1200 degrees Celsius or something, those volatile species will exsolve from the magma and enter a gas phase. They will form a new gas phase, and then they will enter and accumulate in the gas phase as that pressure decreases. And now I'm looking at one of these bubbles. So what does that gas phase look like as a function of the very lowest pressures, right, in the moment that it gets erupted? And the gas species and the relative relationships to one another looks like this chart on the left, where I've got hydrogen species in warm colors, carbon species in green colors, and sulfur species in blue colors. And you see that there's a change, right, in the relative abundance of each of these species as you go from high pressure, this is 1,000 bars, up to 1 bar, right, surface conditions. And the important thing to pay attention to is the sulfur gas phase in blue, which I've made kind of extra bold lines. And in particular, hydrogen sulfide in the gas phase is this dark blue line, and sulfur dioxide in the gas phase is this lighter blue line. And what you'll notice is that at high pressure, hydrogen sulfide, the reduced sulfur species, dominates in the gas phase. And at about 10 bars, just shallower than 10 bars total pressure on the gas phase, there's a changeover. That the proportion, the dominance of the reduced sulfur species in the gas phase decreases, while the proportion of the oxidized sulfur species in the gas phase increases. And right at about 10 bars total pressure, they swap so that sulfur dioxide becomes the dominant component, more so than hydrogen sulfide. And that's important because when we look back to conditions that average volcanism might have been occurring at, the average kind of pressure condition of eruption. In the Archean, before we have significant continental crust, if we've got the same amount of water at the surface we have today, then you distribute that broadly over the surface of the Earth, what you end up getting is a shallow Archean ocean, where the bottom of the ocean would on average be about 100 bar total pressure. That's about 1,000 meters water depth. And if in the Archean, we're erupting magmas at the same oxygen fugacity, the same conditions, then we would expect a dominance of hydrogen sulfide relative to sulfur dioxide being emitted into the deep oceans, for instance. And then if all of a sudden we started erupting volcanoes through continental crust and started erupting magmas subaerially, then we finally see this transition to sulfur dioxide being released into the atmosphere as the dominant sulfur species. And perhaps this is the change that took place around 2.4 billion years, so that we've had oxygenic photosynthesis this whole time, but it was just spinning its wheels trying to oxidize hydrogen sulfide to get it in the rock record. And then we erupt it to the surface, and suddenly all that hydrogen sulfide turns into sulfur dioxide into the atmosphere. And finally, the oxygen doesn't have a job to do with respect to the sulfur species, so it can accumulate. That's the idea. And it's a interesting idea, but what we know, or what we knew at the time, and we still know, that I was a postdoc from an igneous petrologist point of view, thinking a lot about how volcanoes degas and the relationship between the gas phase and the magmas and things like that, is that it is true that hydrogen sulfide, sulfur dioxide ratios in the gas phase decrease as you decrease pressure on the gas phase. But what's important is the combined effect of all of these species that get emitted into the oceans or atmospheres. And you see that there are also some significant changes in the proportions of the other species, the balance between carbon monoxide and dioxide and hydrogen and water. And so I thought it would be interesting to try to consider the total gas phase in this kind of idea to see what is the reducing power of these volcanic gases that as a sum, as a combined system, not just the sulfur species, but what is also happening with carbon and what is also happening with water. And in fact, also what at that time, kind of 5 or 6 years ago, was emerging, what's also happening with the magma, because that turns out to be really important. Okay, so the question now is, what's the reducing power of volcanic gases and how does it vary during decompression? And I'm gonna just borrow directly from Dick Holland's work on this topic, where he considers, in this paper from 2002, he laid out the various species that get emitted in the gas phase by volcanoes, carbon, sulfur, and hydrogen, where the carbon dioxide and the carbon monoxide that gets degassed into the atmosphere or the oceans by volcanoes, ultimately these need to be stored as organic matter, reduced and stored as organic matter in the rock record. The sulfur dioxide and the hydrogen sulfide need to be variably oxidized or reduced and stored as sulfates and sulfides in the rock record. And hydrogen gas needs to be stored as organic matter, and it also gets consumed by reducing volcanic sulfur species and can be lost to space. So he lays out very simple reactions that would do these kinds of things, how you take CO2 in the gas phase and ultimately store it as organic matter in the rock record or as carbonate in the rock record, so on and so forth, together with an assumption that about 20% of the total carbon in sedimentary rocks is organic and has been. That's a kind of persistent estimate through geologic time. And what he does is create this F factor, which is the balance of the reducing reactions to store these things in the rock record and the oxidizing reactions, to see whether or not we would use up all of the oxygen that is being produced by oxygenic photosynthesis by storing these components in the rock record. And so the sum of the reactions that he defines in this paper turns out to be this equation here, where if you've got an F value that's greater than 1, that means you've got more of these reducing species, hydrogen, carbon monoxide, hydrogen sulfide, that need to consume the oxygen that photosynthesizers are producing in order to store the components in the rock record on long time scales. And so that would be a reducing atmosphere where your partial pressure of oxygen is insignificant. And if you have an F value less than 1, it's the opposite. That's the condition that would permit oxygen accumulation at Earth's surface. Okay, so we're going to take a look at these rocks drilled from the Hawaii Scientific Drilling Project. As I said, it's drilled in Hilo, Hawaii, on the main island. You can see the 5 volcanoes that make up the island itself, and the HSDP drilled into some Mauna Loa basalts that come down across in this direction to be in Hilo in the submarine environment there, and then eventually drilled into the Mauna Kea volcanic edifice. There are subaerial rocks that they recovered, and then a great suite of submarine rocks. And in particular, what becomes really interesting about some portion of these rocks for me is that some of these, they drilled deep enough such that they were collecting rocks that were erupted in deep enough water that they were undegassed and transitioned to degassing. And so what they end up doing is catching sulfur and water and carbon dioxide degassing in the act. It sounds a little trivial, but it turns out to be really difficult to catch all 3 of those degassing species at the same time, in part because of the relatively low solubility of carbon dioxide and sulfur. These things want to exsolve and degas at relatively high pressures, and water is much more soluble to much lower pressures. And so catching that, there's a narrow window where all of them are degassing at one time. And this is one of our rock collections, it turns out, that does that pretty well. This is what it looks like to capture this in the act. I'm distinguishing here between low and high silica. It's not important for this study, so you can imagine all of these as kind of the same composition. And I'm not going to get too much in detail here for this group, but what I'm showing you is that I'm confident that these record water and sulfur degassing. The idea is that sulfur concentrations on the Y and total iron on the X, that a magma that is saturated with sulfide liquid, which is pretty common, would fall along this black line in this direction. And you can see all of these samples falling off of what we call the sulfide control line, indicating that something else is controlling the behavior of sulfur, and in this case, it's the separation of a free volatile phase where sulfur wants to be in it. And so this is just indicating to us that something different is happening with sulfur than what we would expect from a normal magma. And the thing is sulfur degassing. We've got these nice positive relationships between water and sulfur, indicating that the two are being controlled by the same process, and that's degassing. So it's a great suite of rocks. They're submarine glass. And I can go then and measure the ferrous-ferric iron ratios and then calculate the activity of oxygen from those measurements. And I'm showing you here that activity of oxygen, again, relative to the QFM oxygen buffer. And so this value of 0 is what we expect of normal mid-ocean ridge basalts from the just regular old reduced interior of the Earth. And on the left-hand plot, I'm putting sulfur on the x-axis. And on the right-hand plot, I'm putting water on the x-axis. And what I'm showing here is that the magmas that are the least degassed, which would be kind of on the right-hand side of both of these diagrams, are the most oxidized. And they're pretty oxidized. They're an order of magnitude more oxidized than normal mid-ocean ridge basalts. And what's really interesting, and there were a lot of people, including Yves Moussalam, Roz Hells, Ali Shortle, a bunch of people working in my corner of the world that were beginning to see that this is the case. What happens is that when the magma degasses, when sulfur is involved, the magma gets reduced. The activity of oxygen in the magma decreases, and pretty significantly. This is a 1.5 order of magnitude decrease in the activity of oxygen of the silicate magma, driven only by degassing. Right, so that's essentially saying that a magma has some activity of oxygen at high pressure. When it goes to low pressure, the gas phase is scavenging that active oxygen from the magma and putting it into the atmosphere. That's the key message here. And that as the magma gets more and more degassed, the amount of free oxygen in the magma is decreasing, decreasing, decreasing. Why does this happen? So we can model this. And so here I'm using a thermodynamic and empirical model called Decompress from Alan Burgessay, made available in 2015. And the idea is that I can, with this model, I can take everything we know from first principles about the solubility of these carbon and hydrogen and sulfur species in magmas. And I can mess around with the activity of oxygen of the starting magma and the gas phase composition of that magma, and I can let it degas, and I can see what is the trajectory that these magmas will take in terms of changing the activity of oxygen in the magma itself as the thing degasses. And so the idea then is that we can track for a given melt composition at what pressure and temperature does the melt become saturated with the vapor phase of any kind of component. So when does water begin to degas? When does carbon begin to degas? Things like that. And at equilibrium, the fugacity of a component, carbon, for instance, in the gas will be equal to the melt, and then do a mass balance problem. That's what Decompress is doing here for us. And in that way, we can track how the activity of oxygen changes in the gas phase and also the melt simultaneously. It does a fairly good job of matching these measurements that we've made. The red and the blue lines are fractional and batch conditions. Interestingly enough, it doesn't quite reduce enough. And so there's something not quite nicely coupled between the activity of oxygen in the gas and the melt here, but it catches a significant portion of what we're seeing with the measurements. And how does this happen? Why does this happen? It looks something like this. Here's the case for water. Water degassing is slightly oxidizing to silicate melts. And it's because water is dissolved in the silicate melt. When it gets to low enough pressure, it enters the gas phase here. And then in the gas phase, there's an equilibrium. Some of that molecular water will dissociate to the equilibrium proportion of hydrogen and oxygen. And then again, at equilibrium, if the gas is in equilibrium with the melt, the fugacity of each of those components in each phase has to be equal. Hydrogen has low to zero solubility in silicate melts, and so oxygen is the only thing that can communicate with the melt. And what you end up doing is that the gas phase makes this oxygen, and some of it goes back into the melt, leading to this oxidation of the melt. You need a lot of water. This is 5 weight% water, and you get about a 1/2 order of magnitude oxidation from it. Same thing happens with carbon, much less efficient. Again, the gas phase, when that carbon comes out of the melt and enters the gas phase as CO2, it's going to create an equilibrium proportion of carbon monoxide and oxygen. The oxygen will communicate with the melt, and it's a little bit oxidizing. Sulfur is exactly the opposite. The sulfur equilibrium between the melt and the gas phase is much more complicated because now we've got 5 different species we have to keep track of. But ultimately what happens is that sulfur from the melt enters the gas phase, and the gas phase is constantly asking the melt for more of free oxygen in order to satisfy the gas phase sulfur equilibria. So as long as the gas and the melt stay in equilibrium with one another, you can really significantly reduce a magma by degassing, that you're scavenging free oxygen from the magma to put into the volcanic gas phase that then gets emitted to the atmosphere. And then you can mess around with the full system, and the black line here is the model that would work for a Hawaiian-like degassing magma, where you're starting with a kind of moderate amount of water, lots of sulfur, lots of carbon dioxide. And the point here is to show that anytime sulfur is in the gas phase, the sulfur reducing effect wins, that the sulfur equilibrium in the gas phase, its hunger for oxygen from the melt beats any oxidizing effect that water and carbon are doing. And so this is something that we're starting to understand much better, but the point that is useful for this crowd is that the gas phase from degassing volcanoes is scavenging oxygen from the melts and incorporating it into the gas phase and emitting that into the atmosphere. That's what's going to be important for the end of the talk. So now we know exactly what the melt is doing. We know exactly what the gas phase is doing. We have a somewhat realistic understanding of how that proceeds in actual volcanism through this decompressed model. And so now it's relatively straightforward to calculate this F factor of volcanic gases as we go through time. And that's what I'm showing you here. On the left-hand side is just going to be keeping track of the various degassing conditions. This is the Hawaiian. This is the model that matches the data that I measured from HSDP. Oxygen fugacity on the x-axis here, where we start oxidized and degassing reduces it. Pressure is on the y of all of these plots. And then I'm showing you what the Holland F factor looks like in the middle plot. And then I'm just zooming in this little boxed area here. So what you notice is that the F factor for that present day Hawaiian situation is a value less than 1. That's great because it is consistent with an oxygen-rich atmosphere like we see today. And what you'll also notice that even though we hit that crossover, we start below 100 bar total pressure and we decrease above that. So we are changing our hydrogen sulfide sulfur dioxide ratio in the gas phase. The combination of that plus that the magma itself is being reduced keeps that Holland F factor at more or less a constant value. So rather than there being an increase or a decrease in the F factor because of the switching of that hydrogen sulfide sulfur dioxide dominance, what we missed was the effect on the melt, that the melt is getting reduced, the melt is providing extra oxygen in the gas phase at each step of sulfur degassing, even at the high pressures when hydrogen sulfide would dominate. And so the F factor actually turns out to be constant in that scenario. We can also model degassing from different tectonic settings. So there's mid-ocean ridge degassing, there's arc degassing, right? The FO2s of the magmas, the volatile composition of the magmas, all of that is changing in these different tectonic settings. And it turns out that, again, all of these kinds of volcanism at Earth's surface today are consistent with an oxygen-rich atmosphere. That's great. The arc condition are these, the triangle lines, and the mid-ocean ridge degassing are the circles. What I point out to you here, I've drawn with this gray line, this is the average depth of mid-ocean ridge volcanism in the oceans today. And so this magma starts at 1,000 bar in this, at this condition, and then it degasses and it erupts to the seafloor here at about 350 bar total pressure at the bottom of the ocean. And here's how you see the F factor changing mostly as the result of the dilution of carbon species in the gas phase. But even if we were to suddenly allow that magmatism to start erupting subaerially, this is another way of testing that Gaillard hypothesis about hydrogen sulfide, sulfur dioxide. Even if we were to let mid-ocean ridge basalt like magmatism erupt to the surface, we do have an increase in the Holland F factor, but we don't get close to increasing above that value of 1. And so what's important here is that the pressure of degassing alone in isolation, changing that, cannot change in any reasonable volcanic system that we think of today. It cannot change the reducing capacity of the volcanic gases to begin to permit or disallow the accumulation of oxygen in the atmosphere. So just changing the pressure of degassing is not going to do it. We started playing around then with hypothetical magmas. These are not magmas that we think ever existed or could exist in Earth's condition given the relative constraints. And what turns out to be really important is that you have to decrease the activity of oxygen of the magma below a value of QFM -2 before you start to get these gases that have these F factors greater than 1 that would then consume the oxygen being produced by oxygenic photosynthesizers in the atmosphere. So the only condition really that can make it happen is by getting very reduced magmas here. You got to drop below a value of QFM -2 in order to consume oxygen that oxygenic photosynthesizers are producing. Right, so varying the pressure of degassing does not generate volcanic gases with F factors greater than a value of 1. And so shallowing the pressure of degassing at the great oxidation event in isolation is not an effective mechanism for triggering the rise of oxygen at the great oxidation event. And in order for the solid Earth to be responsible, if you're going to go down this route, what it seems you need is to have change in the average mantle source of volcanism from below QFM -2 to above QFM -2 around the time of the great oxidation event. And again, we go back to this combination of evidence that we're collecting for the difference for any change in the solid Earth oxygen fugacity on Earth on geologic timescales, and there just is not evidence that the mantle sources of volcanism were below QFM -2 at any time in Earth history, let alone at the timing of the great oxidation event here. And so we would conclude from this, we did conclude in a paper in 2017 in PNAS, you can read about all of this there. And we conclude that there's no evidence that this happens, and it requires some other explanation that it might not be the solid Earth in this way that's responsible, at least not active volcanism in the solid Earth would not be responsible for explaining the timing difference here between the arrival of oxygenic photosynthesis and the great oxidation event itself. And that's what I have for you. I'll stop talking now and I could take questions. There's a couple minutes left, I think.
Thanks, Maryjo. That was great. But yes, we can go ahead and open up for questions.
If anybody has them, I gotta get out of my full screen here. Oh, there it is.
I have a question if there's time.
Sure.
Go ahead, Itai. Yeah.
Hi. Thanks for this great talk, Maryjo. I think it's really important to consider these effects of conservation of redox, between the gases and the rocks. What I wanted to ask was about the importance of chemical kinetics of reactions in the atmosphere, right? Because it's not just the F value. I mean, the F value was sort of a proxy for understanding the relative abundance of gases that would react relatively rapidly with oxygen in the atmosphere. And so, going from emitting less of, going from emitting more of those gases to emitting less of those gases in and of itself would make a difference for the dynamic balance of oxygen in the atmosphere, irrespective of whether you crossed the value of 1 or did not cross the value of 1. And so what I wanted to ask was, even if these F values are all smaller than 1, all negative, can a change in the pressure of degassing change the dynamics of oxygen basically in the atmosphere in a way that would favor oxygen accumulation?
Yeah, that's a great point that, like, for instance, that we are not erupting, that we're erupting mid-ocean ridge basalts to 350 bar total pressure means that we pick up those rocks and there are volatiles dissolved in them. What if we just took all of those volatiles out and put them in the atmosphere? And I think that would work in the same direction that we're talking about here, because again, as if we were to let all of the magmas degas completely, again, the gas phase is always asking the magma for more oxygen to satisfy the sulfur equilibria in the gas phase. Like in order to reach that equilibrium condition, it needs more free oxygen from the magmas. So in any case, the gas aliquot being emitted to the atmosphere, the fully degassed gas aliquot is going to be more oxidized always than we were considering before understanding the coupling between the melt and the magma. Does that make sense?
It does,
it's possible you could do it
I mean,
if there was like an enormous amount of carbon. Maybe it's possible that a weight % carbon would change this F factor, but more than what I think. Like a weight % is a lot of carbon to degas, and it's a really rare kind of tectonic setting that creates that kind of magma.
Okay, thank you.
It's possible. It's a good thought. It's possible, and to explore these models at higher volatile concentrations to get at that would be the way to go, for sure.
Thanks.
All right. Do you have any more questions for Maryjo?
And if no one else has a question, I have another one, if that's okay.
Go for it.
One of the directions that I thought you were going in during the talk was, on one hand, you get more oxidized gases being pumped into the atmosphere. On the other hand, you get more reduced rocks being emitted on the surface. What are your thoughts on how that affects sort of long-term, much longer-term oxygen budgets? The kinetics of the reactions of these rocks with oxygen is, of course, much slower than the kinetics of reaction of the reduced gases with oxygen. But what are your thoughts on the overall effect on the surface redox budget?
Yeah, right. Because then we're creating a lithology that has to weather that's more reduced than previously. It is important what I'm showing, this particular case that I'm showing here, where there's this, I mean, we're talking almost 2 orders of magnitude reduction from degassing. This is unique to ocean island settings because you've got a significant amount of volatiles. You've got more carbon, sulfur, water than you have in like mid-ocean rings. But you don't have as much water as subduction zone settings, for instance. And so if we look at, so that's kind of the black line that these hotspot volcanoes live between kind of the solid gray and the solid black curves here, where you get a significant amount of reduction, where you'd want to worry about exactly what you're saying. But the dashed line here, this condition, 5 weight % water, 2000 ppm sulfur, this is like a subduction zone degassing environment, and this is where we think we make the continents, right? And the effect is much less dramatic. It's only about maybe a quarter or a half an order of magnitude change, and that's because there's so much water that the oxidizing effect of water degassing pulls on it. It's providing the oxygen, that water to hydrogen oxygen dissociation is providing the oxygen necessary to satisfy the sulfur. So you end up taking less from the magma itself. And I would say on geologic timescales for the kinds of questions that we're answering, probably subduction zone volcanism is the place to really pay attention to in terms of creating the continents that we're going to weather and so on and so forth. And so it's important, but not as dramatically important as I would make it seem by focusing on these ocean island magmas. They're really awesome. The Hawaiian case, there's a little bit here where, like in igneous petrology, there are places you go that we understand very well, and you just add a layer, and Hawaiian volcanism is one of those places that we think we get it. And so making these redox measurements, which are kind of a new thing, that it made sense to go there.
Gotcha, thanks. This is really great, thank you.
Thanks for the questions, those were good.
All right, I haven't received any more any more, anything to the chat. So with that, thank you very much, Maryjo, for giving your talk today. It was a really great addition to our seminar series.
Absolutely. Thanks for having me.
Yeah, and for everybody else, thank you for showing up, and we will see you next week for Dr. France Geraldo Sosa.
Bye, everybody. Oh, I see Mo. Hi, Mo. Bye, Mo.